Okay, hi everyone, it's Samantha. I'm one of the Chem001C SIs this quarter, and I SI for Dr. Deanne Zhang. If you have any questions about this video or any of the worksheets, please comment down below. Or if you don't want to comment down below, please reach out by emailing me or attending any of my office hour sessions. So with that, let's get started. Today we're going to be covering acids and bases. And in lecture, Dr. Zhang covered 15.3 and 15.4, but from what he's already taught, I really wanted to emphasize acid-base conjugate pairs and equilibrium, especially since those are topics that have been rather challenging for some in the past. So the only new information in this video we're going to cover is conjugate acid-base pairs. So if you recall from my last video or from lecture, he covered Bronsted-Lowry acids and bases and Lewis acids and bases. Now, of those two definitions, in the last video, I mentioned you should really remember what the Bronsted-Lowry definition is, because in this class, you guys are going to be using acids and bases in equilibrium, and you want to look at the Bronsted-Lowry definition for that. So if you remember, acids donate protons and bases accept protons. Now, from the Bronsted-Lowry definition, we're going to take that a little bit further, and we're going to look at what happens after in a reaction. So for conjugate acid-base pairs, an acid donates the proton to become a conjugate base, and a base accepts the proton to become a conjugate acid. Now, what does that all mean, or what does that look like? You can look at that in the example below. It's all color-coded accordingly. And if the CH3COOH is your acid and the water is your base, it becomes your conjugate base and conjugate acid. Now, what's important to know is, remember, we're looking at acid-base equilibrium. So what do you know about equilibrium reactions? Well, you should already know that an equilibrium reaction can move both in the forward and the reverse direction. So it's moving forward from the CH3COOH and the H2O to form its products. And from the products, it can also move in the reverse to go right to left in this case. And if you're going to look at it, a conjugate base and a conjugate acid are still behaving as a base and an acid, because the conjugate base, let's look at what's highlighted in blue. The conjugate base, if it's going to behave as a base, it can still accept a proton. And what happens to this conjugate base if it accepts a proton is it's going to become the acid that it's paired to, right? So it's still behaving as a base, just moving in a different direction. Same thing with your conjugate acid. Your conjugate acid is still going to behave as an acid. It's going to lose that proton, donate that proton to become the base that it was paired with originally. So at this point, we're going to go to a sample problem, and we're going to calculate the pKa of 1 molar of an unknown weak acid with a pH of 3.14 in solution, described by the reaction below. So let's look at this reaction. Before we start, you guys remember what your acid and your base is, right? Now let's assign what our acid and base is, as well as what is our conjugate acid and conjugate base. Well, we know we start off with HA and H2O. That becomes H3O plus and A minus. So if you look at the left side, if you're looking at your reactants, what's the acid and what's the base? Our acid is going to donate the proton. So if we look at it, we know that HA becomes A minus. HA donated a proton. This is our acid, and this is our conjugate base. Alternatively, same thing goes with H2O. But this time, H2O is accepting a proton, so it's our base. And what it becomes, H3O plus, is our conjugate acid. You could also look at this oppositely, because you know that this is the acid. It's going to donate a proton to become H2O. Vice versa, you know that relationship applies as well with HA and A minus. Now, before we actually go on to solve this problem, just a little disclaimer, this problem is going to kind of encompass what was also covered in video 1. So if you haven't already watched that video, if you don't yet understand this material, please go watch that video so you guys can follow along with this question. So what do we want to do initially? So the initial thing is we want to be able to build a rice table, right? But let's look at our knowns. So I'm going to share the screen with different screen so that you can follow along with the work I'm actually doing. So we know that pH is equal to negative log of H, right? Well, what information is actually given to us? We know that we have the pKa. We want to find pKa of weak acid, which what's our weak acid in this case? Our weak acid is the HA. So what do we need to find any of this? Remember, we have our rice table. And we have HA, H2O, H3O, and A minus, right? And I'm going to remind you guys that it went aqueous, liquid, aqueous, aqueous. And when we're looking at rice tables, or we're looking at how to use a rice table to calculate Q or K, we want only what's aqueous, right? Because in this case, we're working with aqueous acid-base equilibrium. We're looking at aqueous solutions. So let's fill out what we know. If you remember how to fill out a rice table, R is reaction, I is initial, C is change, and E is equilibrium. So are we given any of our initial values? Well, we know we have 1 molar, we have 1 molarity of the weak acid. That's what's given, right? But do we know anything else? Are we given anything about H3O and A? Not yet. So our initials for these we're going to assume are 0 because we weren't given anything for it. Now, do we know anything about their change? Well, that goes back to the original equation, right? Or the original reaction. So we look at HA plus H2O becomes H3O and A minus. If we look at it, all of their coefficients are 1. So we know they're going to be used up and made by coefficients of 1. So the change for HA is a product. Is it going to get used up or is it going to be made? If it's a reactant, it's going to get used up, right? So we're losing it as the reaction proceeds. So it's minus X. And we're not filling anything out for H2O, right? But H3O, its coefficient is also 1. But it's what? It's a reactant or a product. H3O in this case it's a product. So it's going to be plus X. And same thing for A, plus X. Now, do we know anything about equilibrium? Well, we know the pH, right? So we know the pH and the H, we can calculate for the concentration of H. So the concentration of H they give you is for the concentration of H is the pH at equilibrium, the pH at which you want to achieve. That's your desired. So if I erase this really quick, do we know the relation? If we know the relationship between pH and H, can we calculate the concentration of H given that our pH is equal to 3.14? Yes, we can, because we know that concentration of H is equal to 10 negative pH. And if that's the case, we have 10 negative 3.14. And that number comes out to be 7.24 times 10 to the negative 4. Does that value go in anywhere? Well, if we know that concentration of H at equilibrium is this, well, we can put that in for H3O plus, because H3O plus is essentially our H, because it's just H and H2O. But we're not looking at H2O, remember? We're just looking at H. So same thing. It's going to go down here for the H3O plus. It's going to go 7.24 times 10 to the negative 4. And if that's the case, it's 0 plus X equals this. We know that our X value equals this number. So we put that in here as well, right? Because they're both only x. And if that's the case, HA at equilibrium is equal to 1 minus x. And for the sake of space, I'm not going to fill it in there. But let's go back to our slides. So now we have the chart filled out, right? If we have this chart filled out, now we know how we can use these values to solve, right? So if we're looking at this, how can we find pKa? If you remember from the last video, pKa equals negative log of Ka, right? But do you have a Ka value from this? Not yet, but you can calculate it. So your Ka is equal to your products over your reactants. And if you look at it, we have that becomes 7.24 times 7.24 times 10 to the negative 4. Hence 7.24 times 10 to the negative 4 squared. Those are your products. And your reactant is the 1 minus x, which if you plug it in is this value. And that brings your Ka to be 5.24 times 10 to the negative 7. If that is the case, you can use that. Your third step would be to find your pKa, and you can use that with your Ka. You can use your Ka to find your pKa, which comes out to be 6.28. I hope that all made sense. That's how we solve through that problem, and how a lot of the information you've learned so far is can be combined into one problem. If you have any more questions, please comment down below, email, or attend any of my office hour sessions. And don't forget to sign in using the link in the description box.